Good morning, welcome to the physics video lecture. This is Physics 105A video lecture 18. And we're talking about driven oscillations. I brought in the demonstration last time and we already learned a complex method, which I'm going to review now. And extend. So driven oscillations, and these with no damping, so with no friction. That means we have mass times acceleration equals force minus kx, and then a driving force of t, and the usual substitutions allow us to write this as second derivative plus omega naught squared x is equal to our f of t divided by m, drop the subscript. So the technique to solve this involved letting c be equal to x dot plus I omega naught x. So we had a combination of these quantities that are assumed real, give us this complex quantity, and we turned this into a first order differential equation. Have another look at it, it's a lot of fun. And what we ended up with is that the solution was e to the I omega naught t integral 0 to t f of t prime over m e to the minus I omega naught t prime dt prime plus an initial condition. So that was our solution. And because we had originally defined our complex quantity like this, we see we had to take the imaginary part and divide it by omega naught. So x of t is equal to the imaginary part of c divided by omega naught. And we did a couple of examples. We did one example, the constant driving force. Saw how that made complete sense, and then I assigned a driving force proportional to time, which is also interesting. So I want to do a couple of things with this and then talk about resonance again. So let's briefly talk about energy of the driven oscillator. Energy. Certainly, it's not conserved. Okay, we're putting energy into the system when we drive it. Okay, so energy not conserved, right? Because we're driving it. However, we can ask the question of how much energy is put into the system with this term, not conserved. So what we're going to do is do following. We're going to ask the question, how much energy does the system acquire? How much energy does the system acquire? Question mark. And this formalism lends itself to that in a really interesting way. What we're going to do is redefine this here, namely for infinite times. So we're going to say, suppose we're looking at integral f of t over m e to the minus I omega naught t dt from minus infinity to plus infinity. So that's for all time. And then we can divide, have a corresponding definition of this C right here. Let me consult a moment. Yeah. So we're going to use the complex conjugate of this. So define C infinity complex conjugate squared. Now, what that'll do is it will get rid of this e to the I omega naught t, because when you take a complex number times its conjugate, complex conjugate, you eliminate that factor. E to the I omega naught t times e to the minus I omega naught t equal 1. Okay. So because of that, we can just define that as this integral minus infinity to plus infinity f of t over m e to the minus omega naught t dt complex conjugate squared. Okay. But let's look at this expression here, complex conjugate squared, starting up there. So C squared is equal to x dot plus I omega naught x times x dot minus I omega naught x, right? That's what it means to multiply by a complex conjugate. Yeah, let me just make sure. C star. That's the definition, right? So we multiply that out, we're going to get x dot squared, and then the cross terms are going to vanish. I omega naught x, x dot, minus I omega naught x, x dot. So we're left with I times minus I, which is plus 1, so plus omega naught squared x squared. Good. All we have to do is multiply this by 1/2 m. 1/2 m x dot squared plus 1/2 m omega naught squared x squared. Well, what is that? That's the kinetic energy plus the potential energy. Always remember, we've got our omega naught squared is equal to k over m. So m omega naught squared is just equal to k, and that's what we would have had here in the potential energy. So this, which is the energy, is apparently just 1/2 m, right, multiplied by 1/2 m, 1/2 m c infinity squared. And now I just have to multiply this thing by 1/2 m, or energy equals 1/2 m, and in fact, let's just do this before. So when I square this scalar m is going to come out in the denominator squared. So I'm actually going to be able to have 1 over 2m. 1 over 2m. Get a little clean. 1 over 2m. And again, this expression here. Minus infinity to plus infinity. F of t e to the minus I omega naught t dt squared. So this is how much energy is absorbed. And remember, this was the driving force. Now, when we get to Fourier series and Fourier integrations, which we should by the end of the semester, we'll recognize this as the Fourier transform associated with the eigenfrequency. Okay, the eigenfrequency. So it's only driving forces associated with the eigenfrequency that add energy to an oscillator over time. Okay, so that's a great result. I'm just going to refer to this as the Fourier component of the eigenfrequency. We may not know, we may not have that background yet, but we'll get there. Of the eigenfrequency, or of the natural frequency, right? The natural frequency of the oscillator. Okay, so there's more than we can do with this. So we're going to look at a particular case of this integration here, namely an impulsive force. So the last example here, right, for our expression star, is a force that acts for a very short time. Okay. Suppose f of t acts for a short time. I can call it tau. Okay. So tau is a short time. Yeah, well, what is a short time? How can we say a time is short? Well, remember, since omega naught t is equal to 2 pi, and t is the period, we're talking about a short time, namely a time that is much, much less than the period. We have tau is much, much less than the period. That's the idea. Short time with respect to the period of that oscillator. And in that case, okay, therefore, e to the I omega naught t, where omega naught t is always much less than, essentially much, much less than 1, is approximately equal to 1 plus I omega naught t in this integral here, because the boundaries of integration are going to be so short. Yeah, so what that means is we can essentially ignore this, because this is much, much less than 1. So with omega naught t much less than 1, send this up. And this thing simplifies, because now it's just going to be f of t dt. Okay. Not only does it simplify, it's a real quantity in there. Okay, so now E, right, this is our equation star still, is just equal to 1 over 2m integral f of t dt squared. And since that is very short, okay, we can say that's just 1 over 2m f f delta t, okay, something like that. It's just over a very short period of time. But does anybody recognize f delta t? That's the impulse. Okay, that's the change of momentum equals delta P squared over 2m. So an impulsive force imparts just, something gets hit, it imparts that much change of momentum over 2m. Okay. Something you probably had seen before in the chapter on collisions when you were doing mechanics. Okay. So that's an interesting application as well. It comes right out of here, out of the general case, which is short impulsive force, then it just energy delta P squared over 2m. Okay. And since it's an oscillator, it's just been launched into motion with that amount of energy, and then it's just oscillating back and forth as before. So what I want to do now, from there, we want to take the other extreme. We're going to look at a driving force that is driving the oscillator with the eigenfrequency. So I can leave that up there. Well, yeah, I'll leave that up there. So this time we have to set everything up again. So consult the clock here. Okay, great. So this is an example where the driving frequency is equal to the eigenfrequency. That's going to be a limiting case, so let's just call this example and work our way through. I was thinking this would be a homework assignment. Maybe I'll do it all right here. Let's see. I'm just going to set everything up again. So we have x double dot plus omega naught squared x is equal to f of t over m. And this time, where the driving force is equal to f naught cosine of omega t. And notice, here's the driving frequency, here's the natural frequency. We're going to get the general solution and then ask what happens when we let this driving frequency approach the natural frequency. Okay. So we have to go into our solution again and see, I'll actually start this up right here. So there's our problem, and I'll formulate what happens if omega approaches omega 0. If the driving frequency approaches the natural frequency. Well, I showed you that last time on our demonstration. Approaches natural frequency. Well, let's see. Let's have a look. So again, we know that we have to find c I to the omega naught t integral 0 to t f of t prime over m minus I omega naught t prime. The initial condition is uninteresting, and so we're again going to let it be equal to 0. Yeah, well, let me mention, why is the initial condition no problem at all? Because we're just multiplying it by e to the I omega naught t, right? And then we know that there's a pure oscillation in there that we can always tease out. Okay? So it's really what happens due to this driving frequency that's important. Well, we're going to plug in the cosine. So let's just work on this right here. So we're looking at F naught over M cos omega t e to the minus I omega naught t dt. And since the time is 0 to t there, we've got to prime these. And now you're asking, how do we do this integral? What we're going to do is express this as a complex function, but since we had stipulated that this is real, we have to do the following. Use cosine omega t equals e to the I omega t plus e to the minus I omega t divided by 2. That's real. This combination, this in fact is the real part of e to the I omega t, which is cosine. Okay. So we can take this function into here. But there's a second option, and I think we're going to do both. The second option is to go ahead and put in a complex exponential in here, even though f is supposed to be real. Okay. Then we have to be careful to take out the correct part of the result that we get. So yeah, those are two options. I'm going to put that second option on the homework and we'll get started with this one. Here we have completely remained within the rules of the game, so to speak. So we go ahead and plug that in, and now what do we get? Now our integral looks like we've got the f naught over m. We have the integral cosine omega t, so we have to go ahead and write in here e to the I omega t plus e to the minus I omega t divided by 2, and multiply that by e to the minus I omega naught t dt. Put the primes in later. Well, you can put them in any time. 0 to t. So yeah, we have to pay attention to the boundaries as well. So this integral won't be bad because f naught over 2m, and we have e to the I omega t minus I omega naught t, so e to the I omega minus omega naught t, and then we have e to the minus I omega plus omega naught t prime dt prime. So that's what you're integrating. 0 to t. Yeah, at some point I'm going to hand this off. But let's keep going. Continue over here. By hand it off, I mean leave it for you guys to finish up. But let's go ahead and do this. So we've got our f naught over 2m, and the antiderivative 1 over I omega minus omega naught e to the I omega minus omega naught t, and then plus 1 over negative I omega plus omega naught e to the negative I omega plus omega naught t prime. So yeah, there will be no difficulty evaluating this, but I can already point out something. We're saying, what happens if omega goes to omega naught? Should we put a question mark? Okay. Well, whatever is going on here isn't going to give us any trouble, but over here we see we have 1 over omega minus omega naught in the denominator. So that's where whatever is interesting is going to happen. But for the moment, we'll just keep evaluating this, because this was from t prime equals 0, t prime equals t. So we have f naught over 2m, 1 over I omega minus omega naught, e to the I omega naught t minus 1, and then I'll just add the other one here, plus f naught over 2m, 1 over negative I omega minus omega naught, and then what do we have? Close parentheses there. E to the minus omega plus omega naught t minus 1, close parentheses. So there is our integral. Okay. To complete the problem, we have to multiply by e to the I omega naught t, which is going to change these up again. Okay. And then take the imaginary part. So here's what we're going to do. I'm going to assign this as homework. Namely, we want to take that limit. So homework go ahead and take it from the top, but there it is, and then complete the problem. So find x of t and limit omega goes to omega naught of x of t. So again, x of t is going to be the imaginary part of this whole thing multiplied by that. Okay, so it's just a bunch of elementary operations, but you got to pay attention there. Now, as far as the limit goes, let me make a note here. There are different ways to take it. Some are easier, some are more difficult. I'm just going to demonstrate something about this part right here, okay? For the limit of this part here that I've bracketed, when omega is close to omega naught, we're taking that limit. We've done this before. We can expand the exponential. It's going to be 1 plus the argument minus 1. So it's actually just going to be that argument. So we have this red star here goes to, as omega goes to omega 0, we end up with f naught over 2m 1 over I omega minus omega naught 1 plus I omega minus omega naught t minus 1. Okay. And look at that. These go away. This cancels against the denominator. And so that goes to f naught over 2m times t. That's all that's left. So when you multiply F naught over 2m times t with this, okay, what's the imaginary part going to be? It's just going to be the sine of omega t times t. This is going to be that resonance catastrophe I was talking about, where the amplitude keeps getting larger. This is where we find it. And the imaginary part of c divided by omega naught will then go to at least the part that interests us. Okay, this is the dominant part. Where are we? Okay, we'll go to F naught over 2m t over omega naught, and then out of this thing, you have I sine omega naught t, so sine omega naught t. That's going to be that resonance catastrophe expression. Okay, so that's what's going to remain from this part here. It's going to happen here. By the way, this should have been a plus. Here you're actually going to multiply this thing I omega naught t through. It'll get rid of this one, omega t minus omega naught t. Yeah, you'll pull out, you'll pull out some sine and cosine, but this is the term that grows. Okay, t over omega naught sine omega naught t. And a better way to look at that, here I'll finish with this, right here. We could have our x of t is going to be equal to F naught over 2m. And then you write omega naught squared omega naught t. Good to write the omega naught and the t together. That's a dimensionless quantity sine of omega naught t. And then I will have to write plus other, right? Plus oscillatory terms that don't go anywhere. This is the one that grows linearly in time. And in the limit for large time, of course, it grows catastrophically. So that's our resonance catastrophe right here. Resonance. That's how resonance starts. So if you drive a system, this is what happens. You drive a system with its natural frequency, the amplitude, which is what we have right here, is growing linearly in time. So now we know where that comes from. In our later work, we'll no longer look at what happened right at the beginning. We know what happened at the beginning now, this linear increase in time. Consult the clock once more. Okay, that's not bad. Homework is really just to pursue this in great detail. This is one big problem. We're starting right here. We did this calculation. This here, not just the red and the second one, that is our integral here, okay? And I didn't say it explicitly, but again, we're ignoring the initial condition. That's just a bunch more oscillatory terms. So we're really starting out with the oscillator. It's at rest, and we're just driving it at its resonant frequency. And what we're discovering is that the amplitude grows linearly in time And there's no bound on it because it's an idealized system right here, okay? In reality, something will break. Okay, so the homework x of t, limit x of t as omega goes to omega 0. There's a couple ways to do this limit. I just went to the, the quick way to get to the essence of it. If you do all your multiplications out and then have your imaginary part, it's going to be a complicated expression, and you'll have to tease out what happens. But this will be the dominant term, the one that's growing linearly in time. Good. We'll leave it at that and see you all next time.